For the next part of this lecture, we're going to talk about data analysis, frequency analysis with precipitation data. And we'll talk about some ways where some data sources and information we can get from the government that we use for design. So precipitation, frequency analysis. We're going to use these drawing tools here to do that. What we're trying to do here is we're trying to find the probability, which we'll say lowercase p, that some rainfall depth will be equaled or exceeded. So we're interested in P and we're interested in this rainfall depth. So we need rainfall data to do this from a rain gauge ideally, or something similar like that. And a rule of thumb is we need about 10 years of data to do this. And this could be, usually it's going to be something like an annual maximum series, but we'll also talk about a different kind of series of data. And also part of this is we want to specify a duration for the storm. We're talking about it now, we'll be talking about it later. The duration is a design parameter. We've got a probability, a rainfall depth, and a duration, and they're all kind of connected. Shorter duration storms are typically more intense, more inches per hour. There's design considerations we have for short duration storms. Longer duration storms, less intense. We have design considerations for long duration storms. When you do your modeling projects, you're gonna be estimating the peak discharge out of a watershed, and we want to put in different duration storm events to figure out which one's going to give us the biggest peak. All right, so that's one reason to look at different duration storm events. Another is simply because if it's a roadway flooding, if it's a culvert, a parking lot, we want to look at different durations of storm events to understand how they would behave. If we're interested in water quality questions, we're interested in short events, but also what does it mean to have a 24-hour storm or a week-long storm for our runoff or erosion control and that sort of thing. So the different duration storm events are going to play out in your designs in different ways. But if we pick a particular duration, then we can cut our data up based on that duration and then do this frequency analysis. But for our purposes, we're going to kind of stick with 24 hours a day. It's easy to measure things in day-long increments. Although if you stop the clock at 24 hours or midnight, then you might be splitting a storm up in half. So that's something to consider. All right, another kind of way to phrase this is say we can choose a probability value. Often might be 10% or 1% annual exceedance probability. So the probability in a given year that some storm event will be equal or exceeded in terms of depth. And then we want to find the precip depth that is equaled or exceeded with that probability. And that would be in a given year, typically. We've defined this P, this probability, annual exceedance probability. We did this in stats, but we'll do it again here. I think that's an E, but sometimes I put an A. And let's let X be the annual maximum rainfall depth in a given year. So we have a year, we're measuring over 24 hours. Got to specify that duration. So every 24-hour period, we're measuring the maximum rainfall depth. And so X is our random variable that follows a probability distribution. And we'll define this probability, lowercase p is equal to the probability that X is greater than or equal to some rainfall depth. I'm going to say Q just because I don't want to use P again, but this would be some depth. The probability that X is greater than or equals or exceeds some depth is our lowercase p here. So usually we designate this P and then we find what X is, or Q in this case. So say P is equal to 0.01 or 1%. Has a probability of Q has a probability of being equaled or exceeded 1% of the time. We can do the recurrence interval. Ri. Does anyone remember how to calculate the recurrence interval based on P? So we usually use that's a time thing. If we just go 1 over P, we get T. And so 1 over 0.01 is equal to 100. And so that's where we get our 100-year recurrence interval or 100-year event. I like to use probability because this is more accurate. We have a 1% chance of seeing this depth equaled or exceeded each year. So again, P is a probability that some design depth is equal or exceeded in a given year. So we can find this depth based on P using what's known as the Weibull plotting position or this formula. So we'll do that now. All right, so now that we've chosen P based on design considerations. We talked about that in that lecture where we had the internet trouble. I had the internet trouble, not we. And so if you listened to that, hopefully you did, we talked about different approaches to design, risk analysis, that kind of thing. So if we choose a particular probability, we can calculate the risk that this event will happen. And we can do some kind of economic considerations, that sort of thing. So we would choose P, and these are typically specified. So City of Grand Junction has a design manual in which they say, okay, culverts for county roads or whatever kind of secondary roads have to pass the 10-year flood events at a peak discharge. They have to convey that through the culvert. And then if we have 100-year flood events, then that can overtop the culvert and the road, but no more than 1 foot. Am I getting that right, Jesse? Something like that. Yeah. So we can design everything such that we meet these different p-values, right? These p-values are, so a particular design might have more than one p too. So it's in this case, in the City of Grand Junction culvert example, it's the p is 10% and 1% for two different design components. Okay, so we've chosen p. We can calculate Q, or in this case, our rainfall depths. I know we use Q for flow, but I don't want to use P again, so we're going to say rainfall depth based on data. Using the Weibull plotting position formula. And that simple equation is P is equal to M over N plus 1. M is the rank. And that goes from, so 1 is the highest value in a data series. And then N is the number of years if we're using an annual series, number of years. And so this is going to be our probability. So how does this work? Say we have a record of annual max precip depth over a 24-hour period. And that could look like this. We have P in inches. We have rank, which you can do in Excel. We can use the Weibull plotting position formula, M over N plus 1. And then we can also just calculate T, which would be 1 over P, and that would have units of years if this is an annual series. So here's our precipitation. I'm just going to give you some data to kind of just show what this could look like. The rank, this would be 1, 2, all the way down. Say we have 50 years, so 49, 50. So N is equal to 50 years. And then we can use this Weibull plotting formula. So this P is independent of the values. We're just saying the values, we rank them, we order them, we calculate the P just based on the rank and N. And then we see what the associated rainfall depth is. So based on this, we have 0.02, 0.04, all the way down to 0.96, 0.98. And then we can get the recurrence interval. So this is P in this case is annual exceedance probability. T is just 1 over P. So this gives us 51, 26, 1.04, 1.02. So now we've calculated the recurrence interval, T. And we've calculated the annual exceedance probability just based on our data. Very simple spreadsheet exercise. So the 0.02 annual exceedance probability, or the 2% annual exceedance probability, is about the 50-year recurrence interval of that. This obviously has some more decimal places that we're not showing, but 0.02, 2% is the 50-year event. So I want to talk about two different kinds of data series, and you'll work with these in your homework. We have the annual maximum series. And this is for a particular duration. So 24 hours, could be 6 hours, that kind of thing, right? And these are just time windows that we're summing up precipitation. Ideally, you could, if you just had like hourly data, you could have some moving window and figure out a way to like find the maximum storm so that we don't just cut it off at midnight. But you get the idea that we would just discretize our time series into whatever the duration is, sum those up, and then find the maximum. So in this case, n is equal to the number of years. And if we just had a time series like this, we'd have p inches, we'd have, say, 2015, 2016, 2017, and so forth. And each year we would just have one event. It's just the maximum event. And that would be our time series, just like we saw before. We could put it in a spreadsheet. We also have what's called the partial duration series. If this is AMS up there, this is PDS. Annual maximum series, partial duration series. No partial derivatives, don't worry. The way this works is we define a threshold. And for rainfall, let's say, maybe it's what depth of rainfall is important for you, important for generating floods. It could be, we'll take the whole series and we'll take the minimum of this annual maximum series. So we'll just take some threshold, it's based on our data. And we'll just pick, in this case, we'll say 0.5 inches is our threshold. And now in this case, n is going to be equal to the number of events above the threshold. So we'll have more than one event per year potentially. So now we've got this time series, P in inches, we've got our years. And now we could have many different storm events. So here's, let me draw that threshold at 0.5 inches. Say this is the threshold, 0.5 inches. Each year, and for the AMS, we'll take whatever the maximum is, above or below 0.5, it doesn't matter. But now we've got this event, but we could also have this event, right? It's not the maximum, but it's right next to it. Here, we didn't have anything that exceeded the threshold. Here, we had 3 that exceeded the threshold. Here, we only had 1, everything else was below that, right? And so forth. So now we can have a larger N, which means more data. So that's nice. More data can help us do more accurate estimates of precipitation events because it could be less variable. The more data you have, your standard error goes down. So we'll look at a comparison of the partial duration series to the annual maximum series. And if I plot those data, I've got P here, annual exceedance probability. Notice that it goes from small, from large to small here. So this would be 2. So we have 2 events per year. The recurrence interval is 0.5 years. And then here we have 1% over here. So really big events. Where is it? There it is. Okay. The black is the annual maximum series. The blue is the partial duration series for a 24-hour event. And what we see here is obviously the annual maximum series stops at 100% or just before 100%, right? Because we only have 1 event per year. And so we can only estimate a P up to like 0.99999. So this is our 1-year recurrence interval event. And then here's our partial duration series. You'll see how they converge, and they converge right around 10 years, theoretically speaking. This data set looks like it converges a little bit before that. But anything above the 10-year event, the partial and the annual maximum series are effectively the same. So that's from a theoretical standpoint. Obviously, the data are a little more variable there. But everything below that, if we're interested in designing something to a really frequent storm event, a 10-year event, or a 5-year event, that kind of thing, then the partial duration series gives us more information. It fills in the gap. And for a given event, we get a higher rainfall depth. So rainfall depths on the y-axis. If I'm out here and I'm looking at the 2-year event, I get a slightly bigger depth here than I would from the annual maximum series. That's because I have more data. I just have more information to fill in, and I have more storm events that raise the bar for that particular more frequent event. And here's the theoretical convergence there. This is from the book, from one of your readings. And this is the partial duration series line. And here's the annual maximum series line. You can see how the math has them converging at about the 10-year recurrence interval. So in your homework, you'll actually do this, you'll make these graphs. You'll make a partial duration series, an annual maximum series, you'll plot them. Note that we have just P, this is from the Weibull plotting position, or T recurrence interval, that's just the reciprocal of that on the x-axis, and rainfall depth on the y. The last thing I want to talk about, and hopefully we can save 5 minutes to do, the assignment together, is intensity, duration, frequency curves, also known as IDF curves. These are the standard design curves that you'll use to identify the rainfall intensity or depth for a particular duration and a particular frequency. So they combine a lot of different information. So it's the same idea as what we just saw, but for all the frequencies together. And so I'm going to draw it out here. We can have rainfall intensity. Often that's a design parameter. It could also be depth. Intensity would be inches per hour, for example, but it could also just be inches, and which would be depth. These would be different curves, but I just want to note that we could have two different things on the y-axis. On the x-axis, we have duration, some sort of time, and we could get 15 minutes, 30 minutes, 1 hour, 6 hours, 24 hours. The data will go all the way out to a week in terms of duration, depending on where you're looking at. And then lastly, we have our frequencies. And so these are the curves where we get our p-values, our recurrence interval. And so this could be our 10-year event, 10-year recurrence interval, or 10% AEP. This could be the 50-year, and this could be the 100-year. So it's the same data essentially from here, but now we're doing a bunch of different durations and different frequencies. We're putting them all together into one really informative figure. And we'll see this in, I think, a homework assignment later, but these curves can be represented graphically, and you would just say, okay, I want to design something for the 1 hour storm. So I'm going to go up to 1 hour and the 10-year recurrence interval. So I'm going to come over, sorry for that, and then get my rainfall intensity or depth from that curve. We can also represent this as an equation, and so they can fit these smooth lines to the data. And that equation typically has the form of I for intensity is equal to some parameters, A, T, which is our duration, plus B. So these would be fitted parameters. from a guidebook. So the City of Grand Junction manual will give you the figure. It will also give you this equation. And you'll have these different intensities. So we'll have different equations for different p values or frequencies. So we'll have the 100-year storm event. We'll have these parameters. The 50-year will have different parameters. The 10-year will have different parameters. Let's look at some examples real quick. Here's one. Duration in minutes, intensity, inches per hour, and then return period in years. And you can see how as we go to more frequent storm events, the intensity goes down. But as we go for shorter durations, the intensity goes up. A shorter duration of storm event is going to have higher intensity, longer duration events, lower intensity. We can use this data product to do this, to get this information, and you'll do this for the homework. So it's called NOAA Atlas 14. The atlases, have you seen atlases? Do you ever, I don't know, I grew up with these huge atlases and they had like maps from the, major grain exports by a country and, precipitation, right? Atlases are just big maps. And so back in the day, you would pull up your Atlas 14, a big map for your state, and find the isohedral for a particular frequency and duration and get a rainfall depth. Now it's all digitized, which is nice. And so here's this interface that you can use. You can go in, type in an address or a Latin long, and it will give you durations and then frequencies and then depths. So here's the recurrence interval right here in years. Here's my duration. And then I can find the rainfall depth. So the rainfall depth's in bold, and then it gives you a 90% confidence interval for that because it's uncertain, right? These maps work for the whole country, but they're based on point data. So there's some uncertainty associated with that. So you can get your, here's the depth and duration, then frequency, all the way up to a 1,000-year storm event. Alternatively, you can get depth, recurrence interval or frequency on the x-axis, and then here's your duration. So the same kind of information, just presented differently. Here's what that atlas looks like for our state. We've seen this before. And I'll put the question to you all in the last minute we have. Is this a weather or climate phenomenon, what we're seeing here? So this is the 100-year or 1% annual exceedance probability, 24-hour duration precipitation depth. Does that result from weather or climate? Or both? What do you think, Ryan? Yeah, that's not an easy question, right? Is it weather or climate? It's based on long-term data sets, which long-term is climate typically, right? It's also based on storm events, and storm events are manifestation of weather. So I would say it's mostly weather simply because the weather produces these really intense rainfall events, but it's also climate simply because we've got these long-term average data sets that tell us on average, we have more rainfall depth for a 24-hour period at this frequency over on the Front Range and less over here. So the rainfall depth associated with a 100-year event is about 2 inches over here in our area in the Grand Valley, maybe 3 inches a little bit towards the Book Cliffs where the storm events kind of stack up. When you go over to the Front Range, you're looking at 5 to 6 inches, right? So a little bit of both. I actually had this as an exam question, and I think it's a little bit hard to wrestle with that, but What your response was great. I think it's definitely long-term condition, but it's weather that produces these events. Okay, so we ran out of time, but I'll hand this in-class assignment out to you all. And what I want you to do is you're going to calculate the average depth of the storm over the watershed based on first just a simple average, arithmetic average. Then you're going to calculate the depth of rainfall at this point using inverse distance weighting. Then you'll do the contour interpolation method and calculate the average rainfall depth over the area of the watershed. So you'll make your contours, and I gave you this grid so you can count the little squares. So you'll do that and then scan it and turn it in.